Find the moment of inertia of a uniform circular disk. So in the figure you can easily see a uniform circular disk which is passing through its geometrical center. Here geometrical center means the origin itself and perpendicular to its plane and the radius of gyration. Now two things we have to find out. So first of all consider a uniform circular disk which is having mass capital M and the radius capital R. Here the axis is passing through ZZ dash, or we can say the rotational axis is ZZ dash, that is perpendicular to the plane. Now if you want to find out the area of such disk, then it is very easy because this is nothing but area of circle, that means pi r square, and so the mass per unit area of the disk that is equals to sigma. Now the mass of the disk is capital M and the area is pi r square. So here sigma is equals to M over pi r square. Now if you consider such a ring that is consisting of several rings inside it, as in the figure there is shown, this circular disk is consisting of two smaller radius disks inside of that. Now the area of such ring, if we consider a small line element inside the circular disk, therefore area of inside a ring is equals to small a, and that is equals to twice pi, and here if you see the distance between two plates is x or two rings is x, and the element which you have observed is given by dx, so it is x into dx. But if we consider along this equation of density, sigma is equals to mass over area. For this ring I am considered small mass and smaller area, and therefore I can obtain its mass as sigma into A. But what was the value of sigma? The sigma is having the value M over pi r square, and the value of A from equation number 2, that is twice pi x dx. So here pi is cancelled out, and so the value of small m is given by twice mx divided by r square into dx. Now let's find out the moment of inertia of such inside a ring. Therefore, the moment of inertia of the inside a ring is given by di is equals to mass of the ring into the radius of the ring and its square, that means m into r square. Here the mass is given by twice mx over r square into the radius of the ring is x, so it's square. And now if we integrate this equation, that is equation number 3, then we can get the total moment of inertia along this uniform circular disc. But what will you consider as upper limit and lower limit? So we have to take the limit in terms of its radius. The radius is starting at this point at 0 means origin, and it ends with the highest value of capital R, and so the moment of inertia of the uniform disc, I am denoting it as capital I with upper limit and lower limit 0 to R integration di. Let's substitute the value of di is twice mx cube, because x into x square is x cube, over r square into dx. That is equals to twice m over r square is constant with respect to small x, and hence I can take it outside the integration. Now the integration of x cube dx is given by x to power 4 divided by 4 from 0 to r, and which is equals to twice m upon 4r square into x to power 4 0 to r is equals to m upon 2r square in the bracket r to power 4 minus 0. So the final answer will be m over 2r square into r to power 4, that is equals to 1 by 2 mr square. So this is the equation for moment of inertia for uniform circular disc. Now in order to find out the radius of gyration, what we will do? We compare this equation with I is equals to mk square. Therefore the one side is I is equals to mk square and the other side is I is equals to 1 by 2 mr square. So what is the value of k square? K square is having the value 1 by 2 r square, and therefore only k is having the value r upon root 2. So this is the radius of gyration, and with this our illustration number 8 is over. Now let's start the next illustration. Starting the illustration number 9, in which we have to find out the moment of inertia of a disc with uniform density, and it is rotating about an axis coinciding with its diameter. So first of all we have to choose the axis which is coinciding with its diameter, and that is the z axis I am taking over here. But before that, let's determine some important parameters. The first is mass of the disc is capital M. Then its radius is small r. Here it is not described. And if you clearly see that the z-axis is perpendicular to the plane of the disc, only the z-axis is perpendicular, and so we can find out the moment of inertia about such kind of axis with the equation that I is equals to mr square by 2. So here the plane what you will be considered, that is xy plane, in order to define a planar body. Means here we will apply theorem of perpendicular axis, and for that I am supposing something. The moment of inertia in z-axis is I subscript z. Similarly, in y-axis it is Iy, and in x-axis this is Ix. But according to the theorem of perpendicular axis, the value of moment of inertia, that means I is equals to Ix plus Iy, and here the disk is symmetric about x and y because it is having the uniform density. Therefore, Ix is equals to Iy, and hence the value of Iz is equals to twice of Ix. But we have determined in the equation number 1, this is equation number 1, for which Iz is equals to mr square by 2. So substituting this value, mr square by 2 is equals to Ix into 2. So in order to find out the value of Ix only, then we should have to take this 2 into the denominator of another side, and hence Ix, which is very equal to Iy. So the answer will be mr square by 4. So this is the end of illustration number 9. Now we will solve one important illustration in which all the analysis we have performed will be attempted. Starting the new illustration, illustration number 10. Actually, this is the recollection of all the above discussed theories. Here the mass of a hollow cylinder is given 4 kg and its radius is provided by 0.1 meter, which is capable of rotating about its geometrical axis, that means its origin. Now by winding a thin string around the cylinder of a force of 50 Newton, then at the free end of the string tangentially to the cylindrical surface, so it starts rotating, and the first question is asked that you should find torque acting on the cylinder. So the torque acting on the cylinder is given by tau is equals to r cross f is equals to rf sin theta. Now see, it is given that the force is applied to the tangentially of cylindrical surface, and hence here the angle between position vector and force vector will be 90 degree, and therefore the magnitude of torque is given by Rf because sin 90 is 1. So the value of R is 0.1 meter and the force is having the value 50 Newton. So the value of torque, means magnitude of torque is equals to 5 Newton into meter. The second thing which is asked us to find out the angular acceleration of the body. That means we have to find out alpha. So for angular acceleration, we have one relation that tau is equals to I into alpha. But as we know, I is the moment of inertia and is given in terms of mass and radius in terms of mr square, and here the alpha is as it is. Now substitute the known values. So the tau is having the value of 5, mass is given 4 kg, r1 square means 0.1 square into alpha. Therefore, alpha is equals to 5 by 4 into 0.1 into 0.1. And so, the answer what you will get is 125 radian per second square. So, this is angular acceleration. Don't forget to write down the unit because the unit is consisting of 1 mark. And now the next task is angular velocity. As per the equations for rotational motion, we have seen the first equation like this. Omega is equals to omega 0 plus alpha t. But the initial velocity of a hollow cylinder is 0 plus the value of alpha is 125. And the time period which is given to us means angular velocity at the end of 4 seconds. So, the t is equals to 4 and 125 into 4. So, the answer will be 500 radian per second. You can correct in your textbook. In your textbook, the answer is given as 5000, but it is wrong. It is only 500 radian per second. The next one is angular momentum at the end of 4 seconds. So the angular momentum means L is given by I omega. But the value of I is mr square omega. Here the value of m is 4 kg, r is having the value of 0.1 square, and the value of omega we have just obtained, it is 500. And so, if we simplify this equation, then we will get 0.04 into 500, that is equals to 20, and the unit of angular momentum, which is same as the unit of linear momentum, kilogram into meter square per second. Now the fifth one we have to find is rotational kinetic energy. That means E is equals to, we know the relation 1 by 2 I omega square, which is equals to 1 by 2, the value of I is mr square and omega square is as it is, which is equals to 1 by 2, m has 4, r1 square, 0.1 square, 0.01, omega square means 500 square. So the answer or simplification of this will be around 5000 joules. So this is the rotational kinetic energy. The next one means the sixth task is of angular displacement during 4 seconds. Means here we have to find out theta. That is equals to omega 0 plus omega by 2 into t, which is equals to 0 plus the value of omega is 500 divided by 2 into 4. This 4 we have used to apply the time, and so 1 by 2 into 250, sorry, here 500 will come into 4. So 2 to the 4, so the final answer will be 1000 radian. So this much displacement has been done by the hollow cylinder in 4 seconds. Now the 7th task is for work done in 4 seconds. So we know the value of work as tau into theta. The value of tau is 5 into the value of theta for 4 seconds is 1000. So it is 5000 joule. So work done during 4 seconds. Now the 8th one is power at the end of 4 seconds is so that is given by P is equals to tau omega, which is equals to 5 into 500 means 2500 watt. So this is the value of power, and with this illustration number 10 is over. Now 2 tables are given in your textbook which you should have to remember for simple cases, but you can directly give the value in your illustration, so it is not that much important. And the table number 2 is just giving you the differences and similarities between translational motion and rotational motion, which we have discussed in each and every topic wherever it was coming. Now let's perform some more illustration to clarify the more information.